Hello IB. Today we're going to be looking at 15H, the second and the higher order derivatives. So basically we've looked at the first derivative for all the different functions that you know, and we've just found out rules for calculating that. So f dash x is what we call our first derivative, and that's going to be giving a formula for calculating the gradient at any point along our original function. So this is our first derivative. What we could do then is graph our first derivative and then look at the gradient of that function. And when we're doing that, we're taking what's called the second derivative. So we're looking at the gradient function of the first derivative. So our second derivative is looking at the gradient function of the first derivative. So it's the rule for calculating the gradient at any point along our first derivative. Gradient function of f dash x, our first derivative. In the next chapters we'll be looking at what that means and what the significance of that is. So our notation for our second derivative is our double dash or double prime, y double dash, so we can take that shorthand way. Otherwise we can use, instead of dy dx, d2y dx squared. So we've got the 2's here. Now note the 2 goes between the d and the y, so d2y, because we could replace that with our function, the y. Dx squared, we're taking it with respect to x twice. That's why it's like dx squared. And we could keep going. So we could take the third derivative, and instead of doing the triple dash, they put a 3 in little brackets. d3y or dx cubed. So this is our third derivative. And we could keep going. We could take the fourth derivative, the fifth derivative, etc., until we can talk about a general form as the nth derivative. dny dx to the n. So this is the nth derivative. So depending how many degrees the function has, what order it is, depends how many derivatives you can take. So here, if we've got d2 y dx squared, basically this part here is our y, and we've replaced the y with our x squared minus 2x. So that just means we now want to take the first derivative and then the second derivative. So we want to take the derivative of, now differentiate this to give us 2x minus 2. So we've just differentiated that to give here. So that's the derivative. Differentiate that, and now we differentiate it again to get our second derivative. So the derivative of 2x minus 2 is simply 2. If we wanted the third derivative, of our function y, then what's the derivative of 2? 0. So let's look at another example. This time, let's start with a higher power, x to the fourth. And we know that an x to the fourth graph can either be, it could be a really wide graph like that, or it could be an up, down, up graph. That's what the x to the fourth graph will look like. So I've just plotted it on here so we can see this one's linked up to that graph. So now let's take the first derivative of this. F dash x will become 4x cubed, just using all the rules that you should know by second nature now, minus 5x squared plus 2. I'm going to make that 3 look a little bit more like a 3. That's better. Alright, so now we can see that each time our powers are dropping down. So we've got x to the fourth becoming an x cubed, and then that graph is going to look like this one. So we can plot that onto there. And we see we now have that cubic. So that's going to come down here, and I'll change that in a moment to get a proper, let me change it now. And so we can see whether, okay. So now we can see that other minimum. It's come down here at almost minus 30. So that's our first derivative. And if we start to think about this, this is telling us we've got a zero gradient. So this is our original function. This is telling us the gradients. So at this up to here, we have a negative gradient because it's below. Then at this point, all right, we then start getting a positive gradient, a zero gradient and a zero gradient, and these are positive gradients. So that's not immediately obvious. Let me have a check on it. All right, now it's looking really good. So now we can see that we have this negative gradient, which corresponds to this part of the graph down here. We've got a zero gradient here, here, and here, which is our minimum, our maximum, and another minimum. That's our zero gradients, the horizontal tangent. Up here, it's all a positive gradient, so we've got a little bit of positive gradient here, and then we go negative gradient again, so all of this is down the negative region. And then after this zero, that's that corresponding here, we've now got a positive gradient again. So we can, I'll line that up a little bit better. So we can start to explain our shape of our curve by the gradient function. But as I said, next chapter we do lots of this. So let's now take the second derivative. So we differentiate again, just using our same rule. So we've got 4x cubed becomes 12x squared minus 30x, and our plus 2 disappears. Let's graph this one. There we are, that can come onto our graph. And see, we're going from a cubic down to a quadratic. So this is telling us we've got a zero gradient here and here on this graph. So there's our maximum and our minimum, which are the zero gradients. Up here, positive gradient, positive slope. Here, this region all is telling us negative gradients. So there's all our negative gradients here. Zero gradient at that minimum, back to being positive is all there. So you can then predict if we get to our third derivative, if we've gone down to a quadratic, and this time, of course, we're going to come down to a linear. So we've got 24x minus 30. And we can graph that up onto the next one. And then once we've done that, our fourth derivative would just be a straight line. So there's this graph here. I've lined up the axes for the x-axis. That's why it looks a little bit out of scale. So the fourth derivative, if we wanted to do the fourth, remember the little 4 goes in brackets, is going to put x. All right, tidy it up. So our fourth derivative there, the x will become 24. And what's our fifth derivative? Correct, if you've guessed that, it's going to be 0. All right, so we can just keep going. So let's do an example here. Let's get the second derivative, and don't forget to rewrite this in a way that makes it easy to differentiate. So we've got x to the fourth minus 7, and we've got x to the minus a half, because it's the reciprocal and the square root. Fourth, taking our derivative will be 4x cubed. You could always pause this and have a go yourself, and then turn it back on to check your answer. So we've got minus 7 times minus a half, x to the minus 3 over 2. If we're after the second derivative, leave it like that. Don't tidy it up yet. let's take our second derivative now. So we've got 12x squared, and we're going to have, that's going to become plus 7 over 2 times minus 3 over 2, x to the now minus 5 over 2, which is equal to 12x squared, and we've got minus 21 over 4, x to the minus 5 on 2. Let's use our maths manners and turn it back into the way we were given it. So we've got 12x squared minus 21 in the numerator. In the denominator we've got 4. Now if we've got negative, means in the denominator we've got a square root of x to the 5th. Oops, sorry, there's that one down there. All right, the next one here I want to run through. This example is in your textbook, so you can look through that if you want another example, so you can see your textbook for that one. Let's do one that's similar. So now we want to find, there's our function, f of x is cos of 3x, and we want to find the value of the third derivative of the function at pi on 9. So let's just go doing our differentiation. Remember, the derivative of cos becomes minus sine of 3x. Now we need to multiply it by the derivative inside with our chain rule, times 3. So we've got minus 3 sine 3x. Now let's get our second derivative. I'm just going to do the times 3 at the beginning, so we're going to go minus 3 and we're going to multiply by 3 again because that's the inside part. Derivative of sine x is cos x. So it's cos of 3x, and then we differentiate the inside to give us that 3 there. So we get minus 9 cos x, cos of 3x at least. Now we want the third derivative. So we've got minus 9, differentiate cos, we get minus sine x. So we get minus sine of 3x times the derivative of the inside is times another 3. So now we've got minus times minus makes plus, 3 9s are 27, sine of 3x. Then we now want to get the value of our third derivative at pi on 9. So it's going to be saying at pi on 9, what's the slope of the second derivative function? That's what it's telling us. So 27 times sine of 3 times pi on 9. Just do your straight substitution. And we get 27 sine of pi on 3. What's pi on 3? Think back to your triangle, your 60-30 triangle. That's your 60, 1, 2, root 3. So sine of pi on 3 is going to be root 3 over 2. We're in the first quadrant, so it's still positive. So we've got 27 root 3 over 2. Alright, the last one I want to look at is this one here. I'm going to leave that for you to do in class. But if you can, well, we want to talk about it in class. So if you want to have a go at that now, and we want to find the second derivative at pi on 8, and there's an interesting factor about this one. So have a go at that and see what you come with to class. So make sure you've got some good notes, bring any questions that you may have, and thanks for listening. Bye for now.